Hey everyone, today we're going to be going over, presumably, like, polar form of complex numbers. I don't know what it's actually called, but it's, like, pretty close to polar form. So, it's more like a vector, but we're going to go over it anyway. I just don't know what it's called. So, let's say we have complex number z is 5 plus 4i. If we were to graph this on the complex plane, that is the wrong brush. Okay, look at this. We had 1, 2, 3, 4, 5 on the real axis, and then on the imaginary axis we have 1, 2, 3, 4. We could of course plot this out, get a little dot about here, but in order to essentially rewrite this in from what is initially rectangular form, where we have 5 plus 4, that's rectangular form, well, polar form, which is essentially like a set of directions to describe how you get to that little point in the complex plane. So rather than describing it like this, we want its distance from the origin and the angle it makes from the real axis, going counterclockwise, just like on the unit circle. So if we want this set of directions, a new way of essentially plotting out complex numbers that is much closer to a vector, we will, obviously, as I said it, we need its distance from the origin and the angle it makes with the real axis. So in order to find the distance from the origin, we can, of course, construct this little right triangle here, as this point is perpendicular with the real axis. And we have this hypotenuse, which we can find the length of. And that would get us our distance from the origin. So of course, in order to do this, we need the Pythagorean Theorem, and essentially we all know that. So it's just, in order to find the length of our hypotenuse, or length c, I don't know why I labeled it h, it should be c, we would need the square root of a squared plus b squared, and this will get us just c, because the square root and the square cancel out, leaving us with just c. So we have 5 plus 4, I, and we can just leave out the I in this case. We're just looking for distance. So it doesn't make sense to have negative distance. So we would have, well, 5 squared is 25, so, oh, that is bad. So we would have 25 plus 16, and of course this would get us the square root of 41, which is approximately equal to, so just do 41 square root, and that's approximately 6.403. So 6.403. Now that we have our little distance from the origin, we'll label that c. We now want to find the angle it makes with the real axis. So we have theta, we'll describe this as angle theta, and we're searching for that. So in order to do that, we need a little bit of trigonometry, and namely the arctangent or tan inverse function. But in order to do that, we need to first do tan of theta. So what tangent does, it's the opposite side on the adjacent side, which is, in this case, it's just the real axis. So the adjacent is the real axis, and the opposite side would be its, I guess, height on the imaginary axis. So we know what the height is on the imaginary axis. That's just 4. So you would have tangent of theta. Tan of theta is equal to 4 over 5. We have opposite on adjacent, because we know the real axis, it goes up to 5 here, and its height is, 4 on the imaginary part. So we get 4 over 5, and now what we want to do is, I say tan inverse of tan of theta. We know tan of theta is just 4 over 5, so in this case we would then get tan inverse of 4 over 5, or 0.2. Tan inverse, did I just say 0.2? Not 0.2, 0.8 is what I meant. Tan inverse of 4 over 5. In this case that's 0.8, so we can do this. So now what we're going to do is 0.8, and then we do tan inverse on this calculator, because I didn't really plan this out very well. And that gets us approximately 38.659. 38.659. So now that we have both the angle and what the distance from the origin given by the length of the hypotenuse, we now have a new way to define our complex number. Rather than in rectangular form where it's given 5 plus 4i, we can now define our complex number as a set of directions, essentially. So we get 6.403, which is our distance from the origin, and then that's one part of the, I guess, instruction set here. The other part is the angle it makes with this real axis, so 38.659 degrees. Now, actual polar form does this in radians and uses sine and cosine and some more advanced trigonometry and such, and I didn't really feel like learning that. And I also just know this is a lot easier, even if it's not, actual polar form complex number. It's more like a vector. But now that we are given this, we can say, well, we can go 6.403 distance, like away from the origin, and also given this little angle, this rotational aspect, where we would have to rotate 38.659 degrees from the real axis and then go 6.403 in the away from the origin, and that gets us our new complex number, or our, I guess, old complex number with a new way of defining it. So that's essentially how you would convert rectangular form into polar form. There's more complex arithmetic you can do with that, but I'm not going over that in this video. So that's it. Thank you for watching.